Hi everyone. So our next speaker will be Konrad Malawski, who will be replacing Victor Klein. Konrad is maybe well known in Poland as one of the earliest adopters of Scala, and having started lots of communities in Krakow and Warsaw. And now he works at TypeSafe on the Akka library. So please welcome Konrad Malawski, who will be talking about some horrible, mutable things. So let's hear that.
Hey everyone, can you hear me right? Should be okay. So yeah, as introduced, there will be horrible, mutable stuff, but I think for a reason. So this is kind of the goal of the talk, that we're pursuing these asynchronous and scalable systems, and how can we do that and still maintain sanity. So I work at the company soon to be previously known as TypeSafe, and I also work on the Akka team and also did a little bit with the reactive streams where I did the test kit. So with compatibility tests, if you're implementing a reactive streams thing, you're probably running these tests. Other than that, these are the mentioned community things I run or founded or participate in. But yeah, a short question to you guys. I usually have this slide up to see if anyone actually does Scala, but I know you guys do. But I want to know who's actively developing something like a library that actually cares about performance or latency. Mostly library authors, or can be a pet project. Okay, so this talk will be, I hope, very useful to you. And for the others, it's very useful for picking a library. So as you'll see, we'll talk about the things inside, but most often don't really implement these, but it's good to know which library is using which patterns to make an informed decisions then. So this talk is mostly more or less about high performance things, but not in the sense of, oh, look how I'm bit fiddling. So this is not really high performance. I mean, yeah, bit fiddling can help, but it's mostly about high-level fundamental design principles of how you design the grand scheme of things, interactions in a system. This can actually lead to high-performance systems. So that's a very nice quote. I'm not going to read out loud. You can read it for yourself from Martin. And this is the sort of agenda. So I've delivered this talk at also another functional programming conference, and it was basically to troll all the Haskell people with all the mutable stuff. It went great, but I figured that for this one I modified it slightly to be actually useful for you guys. So the first sections are very general, but then we'll actually dive into something that you can use in your daily lives, and we'll see a little bit about benchmarking and how to benchmark and how to not benchmark, and a little bit of tips and what's coming up in future tooling. So yeah, why do we need to go asynchronous, or why do we need to build systems differently than previously? So this is a pretty famous quote from Herb Sutter, C++ guy, that the free lunch is over, meaning that it's getting harder and harder to just slap a beefier machine onto something and it just gets faster. Well, the beefier machine nowadays means more cores or something. So if you can't utilize more cores, it's not going to get faster. So I outlined the reasoning behind this talk, but let's dive into the various topics, and it's slightly disconnected topics, so we'll be jumping around. So synchronous, of course you guys know what synchronous is. So if I send a message, I wait for the reply, then I send another message, and I get the reply. Also known as method calls, for example, right? A synchronous method call with the returning thing coming back. So asynchronous, shortest definition on the planet is I send the thing, and I can immediately after send another message, right? The immediate thing we gain by that is if the second thing is easier to handle than the first one, or faster to handle, we can reply right away. So what this means, we suddenly can have out of order stuff, right? So it introduces that kind of complexity at the gain of we can have lower latencies because we can reply earlier. We don't need to wait sequentially for stuff. But this is the basics you guys all know, I hope. So let's see about an actual problem that we see in our daily lives, which is, well, blocking and scheduling and how it impacts one another. So in my example, I'll be drawing actors, or you can think of them as anything that is processing stuff using a thread or thread-like structure. process. And in this example, I have 3 such actors. They have some mailboxes, and I have 2 actual CPUs. Let's not talk about multi-threading, hyper-threading, and stuff like that. Let's just assume I have 2 cores and some other blocking resource. Could be a database or could be a disk. Doesn't really matter. But it exposes blocking operations. So, because we only have 2 processors, we can only run 2 things at a time. And I'm marking this as painting the blue and yellow lines on the timelines, on the lifelines of these actors. So, as you can see, the bottom one didn't yet have any time to actually do his job. So he's waiting. I mark this as this red line. And technically speaking, every time this actor is taking a message from the queue and it's processing it, it's using the thread, but after it's processed this message, it can technically give the thread back and to someone else, right? Because we're resource sharing. So technically speaking, here the bottom guy has had 3 possible points in time where he could have gotten a thread. But for now he didn't, and now he did, so he can proceed with his operations, whatever they are. And now we have a similar situation that the bottom and the top guy have resources to use, but the middle guy is getting starved, right? So we call this more. So scheduling can be more fair or less fair, right? So if it would be completely fair, then everybody would get the same slice of time to process their stuff. But this is not the world we live in, because we have, well, the JVM, and we can't just preempt the thread like randomly. And the bottom thing is the blocking operation. So the bottom guy called something, either he's writing to a file or interacting with a database with a blocking API, and the thread is kind of wasted, right? And we wait until the database comes back to me, and now I can do something with the result and eventually release the thread. So you guys obviously see that the gray is kind of wasted. So what can we do with asynchronous APIs? We can just tell this resource, whatever it is, that hey, please do this right, and once you're done, please notify me. The same way I interact with the rest of the world, so by messaging, which means that in the gray squiggly line, we're kind of waiting. So yeah, the bottom guy cannot proceed until he gets the response back, but he didn't block the other guys, right? So this is a very simple illustration of what blocking actually means for such resource sharing systems. So here we're happy. Well, also known as, sometimes people think that we always advertise, ooh, never block. So it's kind of true, because blocking is very inherent to many operations on real computers, real systems. So the actual tip we give to people is you need to confine it, right? If you have a limited thread pool that can be basically only used for the blocking things, then it's fine, because you're not blocking on this shared pool that the other guys are using for the fast operations, right? So the hint here is, and the lesson learned here is, you can isolate the blocking things, because you're going to wait on them anyway. You can't get rid of them sometimes in real systems. So it's isolating and not never using, because never using, well, I'd love to say that, but we're in the real world, right? And also, it's actually indistinguishable from being very, very slow, right? So in theory, if the bottom guy would be just processing this message for 5 minutes, the effect is the same, right? So just a few words on what blocking actually means. So what does latency actually mean? And most of us work in systems that, it's highly, well, do we? Who does actually work in a system where you actively talk about latency of your service? Okay, so like half of the room maybe. So let me ask, which of these lines is in your thinking latency, blue or yellow? So this is a queue, and you're waiting to the border control because you're boarding a plane or something out of the UK. So which is latency? Yellow? Blue?
Blue. Okay.
So depends on the definitions you're using, and this is actually the problem I'm trying to highlight. So if you look into queuing theory definitions, so the latency is time to get to the point of service, kind of. And the entire thing is often defined as the entire response time. So the problem with these definitions is that we use them interchangeably in casual discussions. But then in casual discussions it's fine as long as you agree on what it was. But if you're forming a contract and you're agreeing on the latency or the response time has to be this and that, you'd better define it before actually signing a paper, right? So this is fine for casual discussions, but maybe good to know that are you accounting for the service time or not in what you're signing, right? Because it could be, okay, we agree to start processing your request, dear Mr. Something, in this time, or we agree to give you a response in this time, right? Different SLAs. So, another quiz. And if you want to, you can participate with a hands up. So, is 10 seconds latency acceptable in your applications? Sometimes, right? Batch applications, not a problem. 200 milliseconds? Yeah, it sounds good, right? It starts sounding like a web app, more or less. And now it starts to get fuzzy. So how about most responses within 200 milliseconds, right? Okay, who's starting to get a fuzzy feeling that I'm getting somewhere with that? So what about mostly 20 milliseconds and some one minute latency? Like, kind of weird system, but yeah, those exist. So do people die when you go below 200? Could be. I mean, so yeah, these are actually kind of trick questions, and what I'm trying to highlight is that the way we kind of build SLAs nowadays, which is some business guy comes into the room and says, "Oh, I read in Newsweek that 200 milliseconds is the thing, because Google does that, and everything has to be 200 milliseconds." But actually, it's a PDF like generation which no one looks at. So what I'm trying to convey here is that it would be way nicer if we were able to reason about these latencies as a range, right? Because sometimes maybe it's fine to have a pause because it's not that critical and no one will die, but sometimes maybe it's not. And another problem that sometimes I see in the field is, well, actually most of these quotes are from Gil Tenne talk, Azure Systems guy, and from this great talk about how to not measure latency. So if you're curious about any of these kind of things, check out that talk. And a typical quote from developers is, yeah, so our response time is 200 on average, and standard deviation is 60 milliseconds, so I'll use math and figure out, what the max and minimum are, or stuff like that, or what the mean response time is. So, or actually figure out the percentiles, right? Because you have a normal distribution, right? So you apply the normal distribution, you get the latency, you get the standard deviation, you move it a bit to the right, and you have a number. Problem being, the real world does not behave like a normal distribution. It's very spiky, very, very chaotic, surprisingly, right? So you cannot really apply that math, just slap normal distribution on it and figure that you found your 99th percentile. So what you can do, however, is actually measure at such high values. Like, this basically means measure everything, like all the values, and then you can really have all the distribution drawn out. So this is from a tool called HDR histogram, and actually JHiccup, also from Azure, but open source, you can just use it. And it's used for figuring out if I don't know, because I'm trying to benchmark something, but it turns out, like, inherently my system has these hiccups. Like, the system does nothing, like completely nothing, empty application, but it still has these hiccups, right? And this means that you cannot ever be better in latencies than these hiccups, because they occur in a totally empty application. So that's what JHiccup is for. So if you're trying to benchmark stuff, you can't possibly be better than the idle state. So it's interesting to see how weirdly the system behaves in an idle state, actually. And then HDR histogram is, like I described, a tool for collecting proper histograms and a nice way to drawing them. So at the bottom thing, you see, well, there's some elapsed time, and sometimes we have this spike in the latency, right? What does this mean? Well, yeah, sometimes we have a spike in latency, but you can't really reason more about this. Is it really a problem for us or not? However, the bottom graph collects all the latencies, and you draw them like the x-axis being the percentile at which this has happened, and the y-axis being actually the latency, right? And you can see this has this kind of weird shape. So, and you can think of it as modes, right? So this system seems like it has 3 modes. Well, up until the 99th percentile, it's perfect, great, not a problem. But then it starts behaving, you know, weirdly. And then around the like 99.9, between 99.99, it starts behaving again somehow weirdly. So what we should be doing with these things is to actually look into this and try to investigate what the reason here is. So more often than not, you'll find that such curves that are kind of smooth will be some kind of queue buildup, that there is some kind of queue in the system, and it's taking longer and longer to process these things because the queue is growing, right? And if it's more of a like rapid step up, then it will be more like stop the world things. So even by just looking at stuff like that, you can have some intuition. But then you need to apply your intuition from the project. For example, if you see a shape like that, you figure, this looks kind of like a snake. And we have this big snake thing in the system, and it behaved like that, like some years ago. But wait, actually, it's an elephant. But what I mean by snake and elephant is actually not snakes and elephants in the system, but if you build your system and it's composed from many different pieces, and you draw the graphs for all the subcomponents, and then you can suddenly recognize this behaves kind of like the queuing subsystem that we had some trouble with recently, right? And you can see these patterns. So it's about helping us out to figure out where to look, and I'll talk about that a bit more. Quick definition: the right-hand side on such graphs is referred to as tail latency, and we'll talk about cutting the tail latency, because this is actually what you normally want to optimize. So by looking at this graph, do you guys know where we should kind of start looking into, what we should optimize, like any intuition? Because there's a subtle hint on this graph. Because, oh, you probably don't see that. Yeah, that's a SLA. Here we're not hitting the SLA. So it doesn't make any sense to optimize like the usual case. We need to figure out where we went past, right? Because if all of the time we're not hitting the SLA, well then everything is crap. But if on the very right-hand side we're not hitting stuff, then probably slapping on a profiler on it would introduce maybe too much overhead and will impact the graph too much, and we're not fixing the thing we should be fixing. So it's that kind of intuitions. So, lessons learned, precise language helps, and yeah, verify the results and measure actually everything, not measure something and then try to extrapolate, because that's making up data. So, we're gonna jump topics, and we're gonna come back to measuring stuff and actually tooling. But for now, let's focus on concurrent versus lock-free versus wait-free. So I'll ask this one from the end. Who has heard of wait-free algorithms? Okay. So I figured this talk should be actually interesting for functional programming, like conferences, because not many people dig into this. However, many people dig into, category theory and stuff like that. So it's an interesting thing to bring up at such a conference. So concurrent data structure, easy. How to define it in layman's terms is basically, if I access it concurrently, it doesn't blow up, more or less, right? But what can happen in concurrent data structures is stuff like that. So you're trying to write, it's some kind of variable holder thing. So many threads try to write, and always the right-hand side keeps winning for some reason. Perfectly fine concurrent algorithm. However, what's the moral here? There's two. So one moral is thread A is a complete loser. It's not doing really good. And the other one is actually more formal, that it may never make progress. Okay, this is only based on observation. Maybe it will, but maybe it won't, based on our observation so far. So the same can actually happen when you just take a lock and wait and wait and wait, right? But let's not talk about these things. Those are no fun. And again, the effect is the same. Thread A may never make progress without even looking into the algorithm. So how to see which APIs to not use. So this is from the one of the concurrent queues in the Java library. And there's multiple ways to put a value into the queue. One is offer, and when the queue is full, it will return false, and then you can, well, either retry or stop putting stuff into the queue. Or there's another one which is more Java-like, because it throws an exception if unable to put stuff into the queue. Or the third one, which you should never use, which is put and it returns a boolean, so kind of like offer. However, it will keep blocking until it has put the thing into the queue. So it basically means this method will always return true because it's blocking until it returns true. So watch out for such smells in APIs. But let's talk about actually fun stuff. So lock-free. So I asked you guys about wait-free, but who's familiar with lock-free algorithms? Yeah, most of us, right? So that's not very hard, but here's a visualization. I always think visualizing stuff helps me. So lock-free means that no one is really waiting for anyone. They are just continuing to go through the system without, there's no lights, there's no traffic jam, etc. And there's even some people. But how does this actually, what does happen if this fails, right? So what the formal definition is, that the algorithm that is lock-free is a program or algorithm that if it runs sufficiently long, that at least one of them makes progress. So in this case, with the cars, you can imagine that sometimes the cars crash into each other. So a lock-free version of that would be, well, you crash into the other car, you back out a little bit, and you try to go through again, and you crash again. But okay, I'll back up again. And eventually, everybody will be able to cross the crossing. With more or less crashed cars, but they will be. So that's a guarantee we have in lock-free algorithms. That's a definition. So how does one look like? Very simple to implement actually, and it's based on the compare exchange operation that is actually internal to modern processors, at least Intel's, and Intel family in general, x86. And what it does, it can atomically compare, and if something matched the expected value, put the new thing in, right? You guys said that you recognize this pattern, so I'm not going to go very deep into it. But another very nice thing we have in Scala for that, actually, is the tail rack, right? Because we can keep recursing in this method until we've succeeded. And that's a very nice thing. Well, by the way, Java people can't do that and need to explicitly write the for loop, right? So some niceties Scala gave for this kind of implementations. Most likely accidentally, because, yeah. But so what does it actually do? You have two threads, they try to write to the black box, they obtain the value from the black box, they prepend their values to the black box's value, so the yellow and the blue thing, and they try to compare and swap. Here, because it's an atomic operation, there's no, there can be no at the same time, like one case will be always before another one. So here the yellow one succeeded, and which means that the blue one will fail and will retry, and now it has succeeded. So this is the retry loop. We call this very often spinning and just retrying as fast as you can. And you can of course build in like backoff strategies that, well, if I haven't been able to succeed in a number of times, maybe I should give up, or stuff like that. But let's look at wait-free, and I'm not going to go very deep, because the reason I talk about them here is to show you a spectrum of guarantees we can expect from algorithms. So wait-free has a very strong definition. So it's an algorithm which, I'm going to read this, which has a bound on the number of steps after we have guarantee that we proceed, like make progress. Okay? So there's an upper bound. In layman's terms, it means, well, after at most 5 tries, you're guaranteed to, okay, now it's your turn and we allow you to take the right. Guarantees like that. Where can you see these algorithms? Well, not surprisingly, the Java util concurrent package is very good at those. And the concurrent linked queue, their offer has actually such a bound. And I'm not going to go very deep into it here, but you pay some complexity for more guarantees, as always, as Runa said, right? So let's try to use that to construct something functional. It's a functional conference. So let's try to mutate stuff, but make it look as if it's not really mutating. Okay, the all will just stay there, so we have an extended what moment. So imagine you have this thing that is, I don't know, indexing stuff. Maybe it's a compiler that it's putting like type symbols or something like that into some kind of cache. And this cache is shared because that's the purpose of a cache, right? However, we have this mute method that will mutate the cache, like add values to it, and it returns a yes, succeeded or not value. So we kind of expect that it may fail to do the write. And then we have a method that's called observe. And when you think about it, so referential transparency, kind of fuzzy defined, but more often than not means, well, once I've observed the value, it's always the same thing. So here we have this wrapper thing, and the only way to observe the value is to explicitly observe it, right? Otherwise you don't see what is in the cache. So in order to kind of satisfy referential transparency in that sense, we can build a structure that will happily keep mutating until the first, well, person, thread, whoever, looks at the thing. So the moment you observe the values, they are frozen. So, funny little technique, maybe useful, maybe not. And I actually think Daniel was at some time ago raving about it, how great it helps one of their systems. But technically speaking, it's referentially transparent, at least from the observed's point of view. So, funny techniques we can play around with. But the moral of this story is pick your algorithms as crazy as they need to be, but not crazier, because the weight-free one is kind of complex, and either you want to spend a weekend implementing it, or a week, or you don't, because you don't need to. So, again, different topic. IO, and NIO, which was actually mentioned today. And one which may or may not surprise you is 0, which actually isn't the same thing as the other names, but I still want to talk about it. So, this is an awesome quote from Havoc when I was preparing this presentation a while ago. I was asking for feedback, yeah, do you guys have any idea what should I talk about? And then Havoc, working at TypeSafe, said he worked on stuff like gconf and GNOME and, you know, very UI desktop things, which are very event-driven actually, right? You click a thing, something triggers. So, well, he missed the event loop, well, the IO loop. So, quick interruption about user mode and kernel mode. Do I need to explain user mode versus kernel mode? Okay, maybe let me ask this differently. Should I explain it or not? So if yes, hand up. If no, hand up. Okay, so I don't need to explain. Excellent. So we have these two modes. Switching between them takes some time. So we would like to avoid switching between them all the time. Done. At another conference I had to go like, calm down guys, this is actually happening. So yeah, when does it happen? Most of the time it just means that we cannot do some privileged operation, and the kernel has to do it for us. One of such operations is reading or writing to files or sockets. So when I call read in my Scala program, what actually happens? Well, the kernel will have to perform the read for me. So we switch the mode, and then for the write, maybe I'm doing a copying of files very naively, so reading and writing. And then we have this kit again. So, as you can see, we wasted some time on these mode switches, and they're not the cheapest thing on the planet, so let's try to avoid them. Well, that's actually just half of the badness. More of the badness in this story is actually the number of copies of the data that you have, right? So we all recognize that copying takes some time, right? And useless copying is the kind of copying we would try to avoid. Well, the problem is, because the kernel will read the data into a kernel buffer, it then has to hand it over to user space, which is a user space buffer, so it needs to copy the data to user space. And then, if we write, it needs to copy it back to the kernel space. So we have how many copies here? 1, 2, 3. Yeah, technically 3 times copied, because then it stays in kernel space to a TCP connection, for example. Okay, so how can we improve on that? So one of the solutions is asynchronous IO, known in Java land for new IO, but no one really calls it new anymore because it's been new since 2004. So we call it NIO. And one of the operations it exposes is just asynchronous file IO, right? How does that work? Exactly how we explained with blocking resource thingy on the first slides. So tell to the kernel, hey, do this write, and the kernel will just notify us once the write has been successfully processed, right? And we can still keep doing stuff in user space. So it's less waiting in that sense, but it's the same amount of copying data around. So this is where zero copy comes in. So this was partially a solution to web servers wanting to serve static content very efficiently and trying to avoid the stupid copying of data all around. So let's try to work smarter and not really harder to solve this problem. So the operation, how you'll find it in the kernel, is called sendFile. But if you try to Google for it, search for zero copy, because this is how people most often refer to it, even though it's technically not zero copy but 1 copy, because you send it once to the kernel at least. But the API does it is such that basically you instruct the kernel what you want to do with the bytes, and it does the copying, like the writing internally, right? So no back and forth. It is a blocking API, however. So trade-offs. Which one do you need? So for static content, I mean, this is the... Okay, so lessons learned. Yeah, and that's a funny one on the bottom here. So if asynchronous IO can beat synchronous IO, theoretically, maybe. Practically, I've never seen it. So why could it in theory? Because if you're issuing reads for the same thing all the time, then it could be just read in once and, you know, served many times. However, that's kind of rendered not very interesting because of the way operating systems use pages and page caching. So such effect is not really interesting. And yeah, synchronous seeks hard to beat even on SSDs, right? So finally, some more Scala. It's been not too much Scala right now. So let's go back to function outside until inside, which is where I'd like to pop into a mini quick demo. And the examples I show here are from Jan Pustelnik's talk. That's a guy in Poland, and he did a bunch of benchmarks trying to compare different styles of implementing sorting algorithms. Well, to be fair, this is not a very fair comparison, because sorting, I mean, nice in-place in an array sorting is kind of bound to be way faster than trying to sort immutable data structures, because all of the copying happening. However, let's see how bad it actually gets. Okay, so we have some expectation, but it should be bad to try to sort an immutable data structure without touching it, you know, fiddling around. However, how bad will it be? So there's some functional Haskell implementations, the baseline being the C++, you know, quick sorting C++. Everybody's done that at some point in their lives. And the Scala version will be from Runa's book about the ST monadic kind of, it's like state but slightly better, from the solutions to functional programming in Scala. And I don't mean by any means to bash the solution. I'm just trying to show how you can figure out what is happening. Okay, so we know it's going to be slower. How much slower? First, let's compare the imperative versions. So Haskell imperative, so they try to squeeze as much perf out of it as possible. You can find the reference implementations below. And for 1,000,000 elements, and the other dashes are where it either didn't complete or just Jan stopped waiting, basically. So let's look at the 1,000,000 elements and see, okay, 300 milliseconds, standard C++, 60, okay, to be expected to be the fastest. And then Scala imperative. We are pretty good, right? We're pretty low level. We can do all the horrible things C++ can. So we are doing pretty well here. let's try to go functional. So here you can see we're trying to do functional stuff in C++. It's not really meant to that, and the runtime is, for example, not doing stuff like the Haskell runtime is doing for you when you're trampolining or stuff like that. So it's not that good. But at Scala functional we're still reasonable, and well, even faster than the Haskell version, surprisingly. You can mock the quality of the benchmark afterwards. If there's some improvements or not, feel free to do so. However, let's look at the fully purely functional Scala Z style of we wrap everything in a state and we keep creating a new state, etc. So as you can see, it's getting pretty bad. Not really surprisingly, but what I want to do at this point is to help you guys how you can actually figure out what is happening, right? Because just pointing out that it's slow is not very helpful. So, and we have this tool called JMH. So it's the Java Micro Benchmark Harness. It's developed by, well, the OpenJDK team, and we use it for all their internal collections and, well, even micro benchmarks, like how can we improve addition and very, very like low-level benchmarks. However, for that kind of thing, it also works very well. And okay, so we have a quick bench. I can show you the code if you want to, but reading it is not really very part of exercise. Yeah, and it's huge. Where's the ST version? So actually, this is how JMH looks like. Anyone used JMH already? Okay, so a few. And anyone did hand-rolled benchmarks, like a while loop and system millis? Please don't. Please. I mean, seriously. And I have an example how it's completely wrong. So, yeah, it's very Java looking. It's the Java team. However, what we actually care about is not the API. I don't completely care about the API here. Yes, it's annotations. However, I do care about all the infrastructure that is built into JMH around, well, not optimizing away the code that I'm benchmarking. Right? The JVM is very good at optimizing stuff. So, for example, if you're running stuff in a loop, but it's actually never used, the JVM may suddenly decide, well, you're actually never using that, so I'll just delete that code. And then you see, oh man, my code is so fast, so freaking fast. It's fast as if nothing was happening. Well, maybe exactly that is happening, right? Maybe the code was optimized away. So there's a lot of infrastructure in JMH to avoid benchmarking nothing, basically. And yeah, how does it look like? Yeah, you have a benchmark method, and pro tip, if after this talk you figure out, yeah, I should be using this, do not do this. Why? Exactly because of the thing I just said. Because if the value that I'm returning here is not used, the JIT may figure out, well, you're not ever using this, so I'll just take it out. Maybe it figured that, well, you're just doing addition and you're not ever using the value. Actually, addition is another fun one, which the compiler just can figure out, well, you're adding 2 to 2 or a lot of times, so I'll just put 4 in. And this actually works even with a bit more complex math sometimes. So always return the value, the result of the benchmark thingy. And then you can just run it. So how do you run it? There's a SBT plugin. I know you can't see probably. So there's an SBT plugin which makes it super easy to integrate. You just have a Scala file with the annotations and just run it. So a little bit about why do we have so many parameters here. So I is the number of iterations of the benchmark. So we want to iterate it a lot of times, not twice. Because if you benchmarked it twice, then maybe you hit the happiest case ever twice. But actually it's fluctuating all over the place when you run it many times, because maybe it's doing a lot of memory pressure, and then it starts GCing like crazy after a few times, things like that. So a lot of iterations, and also a lot of WI warm-up iterations. Because what the JVM does, every, I don't know, after how many thousand or 100 times it starts inlining methods. This is actually a heuristic I forgot, but it needs a little time to gather information about which methods are actually hot, so it starts inlining those. So we want this to happen before we start measuring, right? So this is why we need bench warm-up iterations, and then the F stands for forks, which is something none of the other benchmark tools actually encourage you to do, which is a good thing to do. So why do we want to fork, like have different JVMs run the same thing all the time again and again? So the reason is some of the JVM's optimizations are, well, very opportunistic, because it has this time span in which it can try to fit in an optimization, and if it won't make it in time, it won't apply the optimization. And this kind of differs from run to run, as in from JVM run, from JVM run. So we want to run sometimes on different VMs to see if it's actually stable. But here I just wanna, I'll start the benchmark in the background. And what I'm measuring here is the average time, that's benchmark mode, and results in milliseconds. And I'm actually using the profiler GC. So there's a lot of profilers built in, and I'll talk about a few of them, the more awesome ones. So sadly, the more awesome ones, they don't run on a Mac, right? For reasons you probably know, because they need actual support in the Linux kernel to do their metrics, right? So it's not something on JVM level. Some of the profilers are actually on the kernel level. And I'll show you some results from it, but I can't run it on this machine. So, because I'm expecting the ST-monad being very functional and returning the ST-monad all the time, I want to see how much memory pressure is actually being made by it. So, benchmark finished, and what is interesting here is, so it yields of course the benchmark result, which is the average of how much time it took per sorting. So this is sorting 1 million elements. It took more or less 1.5 seconds, with standard deviation around 200 milliseconds. So it fluctuates a bit. But then you get the additional things, which sometimes people, when they find JMH, they just stop at looking at the average time it took to do something. But that's actually not the powerful thing. The powerful thing are all these interesting profilers, which, for example, give me the GC allocation rate. So here we can see we're allocating, is that 2 gigs? That's 2 gigs per second. Is that a good thing to do for sorting an array? No. So we kind of found what the problem is, and then you can figure out using other profilers where is it actually allocating and stuff like that. Yeah, verse is stack-based one. I don't want to spend too much time because I don't know how much time I have. How much time do I have? 10 minutes. Okay, so we'll eventually get back if you want to see the other profilers, but I have some of the interesting ones in the slides. So what I want to urge you to do is not finish benchmarking once you get a number. This is the beginning of benchmarking. I got a number, why is it bad? And then I figure out, okay, it's allocating a lot of stuff. So then you need to figure out, okay, where is it allocating a lot of stuff? And then you need to ask yourself, does it have to be allocating a lot of stuff? If you identified it being slow because of that reason. It could be slow because there's, I don't know, some lock involved and it's waiting all the time. This you'll see.
I was wrong, it's actually -8 minutes.
Oh, okay. So I'll just blaze through. I'll blaze through in 2 minutes then. Because we started late anyway. You know that. Okay. So, sorting, is this a pure function? So we're doing a horrible mutable thing inside. I'll even highlight it for you. So this is a Java array sorting, which is in place. It's a timsort algorithm, and it's doing an insert horrible mutable thing, right? However, what do we do with this method is, this is from the vector collection. It first copies the data from the vector into this array, does the sort in the array, and then returns another copy. So, well, it's a pure function, right? It's just doing horrible things inside, but I don't care. It's doing the fast thing inside for me to be happy as a user from the outside from this function. So, random note on this thing. Yeah, so please don't benchmark using for loops and stuff like that. Random example from the Circa repo I recently chimed into. We're comparing Circa, so that's a Travis Brown JSON parser, was mentioned today or yesterday, with PlayJSON. And yeah, depending on the order in which, because the guy did it in the REPL, And first you run Travis's code, and then you run Play's code. So, ooh, the Play code is so fast. Well, of course it is, because the JVM has warmed up by now, right? So if you inverse these things, just inverse the order in which you run these things, well, actually they're kind of similar, because now it's warmed up. Because, yeah, Circa does some stuff before it starts passing and stuff. So don't ever just slap a number out there on the internet. Always provide some backing why it's slow or why it's fast, because maybe it was optimized away. So other stuff I wanted to show you that I can't show on this MacBook is perf. So JMH provides perf integration. So perf is this tool for collecting events from the kernel. And there you can see, well, how many context switches per second am I doing? Like if you're doing stuff that's interesting for that, or how many branch prediction misses did I have? Like if you have a lot of ifs in your code, are the ifs, you know, does branch prediction work properly with those, or is it always missing? Then you can just fiddle around with stuff and it will be better. And the last thing is perf asm integration, which actually allows you to print what the JIT compiler emitted for your methods, and what the integration does, because this you can do with plain JVM. However, what the benchmarking integration with JMH and perf asm does is it figures out, well, I'll only print the stuff that you're actually interested in, because here it's spending most of the time, right? So it's actually useful versus printing like 5 pages of ASM and trying to find your method in it. So here you can see this compare is taking like 30% of this method's time. Right? So this is how many cycles, and this is how many instructions, like number-wise, are being spent here. And then you can figure out, well, why is it doing that? And if you're curious why is it doing that, there's a nice blog post by Nitsan. There's links at the end of it. And last thing I wanted to show is the recent trend in all kinds of benchmarking and profiling, which is flame graphs. So a flame graph I want to show you, and then we'll probably finish the talk. So this is a very, very old flame graph. However, it fits our purpose for today of showing you what it is. So a flame graph is, again, using perf to collect kernel level like counters, how many times something was hit and how much time it took. And then you can use a Perl script by Brendan Gregg, I believe, to make this graph. So it's an SVG file. And you can, the x-axis is not time, it's not running time, it's a time spent. And the y-axis is stack depth, right? So the higher we go on this graph, it means the deeper we are in some kind of method call, and the wider something is, the more time it took. So we can figure out, this is from the Akka code base, but very old. So here we see, well, for Akka it's to be expected most of the stuff to be done inside the fork join pool. Okay, so we go inside the fork join pool, and it zooms in, and then you can see, well, it's doing most of the stuff in process mailbox. What is actually taking the most time? Okay, receiving messages and handling stuff. This is actually the Akka streams infrastructure, but from, yeah, a lot of time ago. So this looks quite differently now, but you can figure out, okay, so the pump is taking a lot of time, and here it's taking a lot of time creating actors, and the red things are kernel mode spent time. So on this graph you actually see how much better you cannot be, because this is the kernel and not you. So I'll just wrap up. Yeah, this is a mini pitch. So we happen to have a nice performant engine, but as Runa said yesterday, constraining the domain can actually help out a lot. So I realized this is, we're kind of in a great position. So this is the last exactly thing I want to show you, is that we have this graph DSL, and the DSL itself is pure, it's, you know, immutable and stuff. However, once we run it, we use all the horrible things inside to make it fast, right? So userland API, nice and pure. Execution engine, nice and fast. Exactly how you want it. Yeah. So this is the Scala Akka streams DSL. You can look into it afterwards, so I don't want to get too much overtime. And this I'll skip, I guess. So I was kind of adding Scala stuff to the talk, and it grew. Okay, So, last quote, totally last quote. So you don't need to be a great mechanic to be a great racing driver, but it really helps if you understand how the machine works, right? So this is my message with this talk, but most of you don't have to, you know, and I hope not many of us need to drop down to the horrible things all the time. However, it's good to know, well, if I pick a library, is it doing, you know, the efficient things or not? So this is all I had. There's a number of links and a number of thanks. And yeah, thank you. So questions probably during the break or something. Thank you very much.